Welcome. I think I hit something, but I think we're okay. Happy Monday. Okay, so big day. We're starting our last chapter today. So chapter 9 is the last chapter that we're doing. And of course, our last quiz is going to cover chapter 8 and chapter 9. So chapter 8 was last week, and honestly, off the top of my head, I can't remember at all what it was about. Time series, I think. That's what it was. Okay, and so we're going to start chapter 9. Let's see if I can get a pen going here. Today we will start chapter 9. Oh, I said 9, but then I wrote 6. That's weird. Which will be our last chapter. Now, of course. Hey, I gotta make this bigger. Oh, it's not the thing, is it? It's really important. No, not really. So we'll start chapter 9, which will be our last chapter. And then on December 3rd, on the Friday, we have our last quiz. So quiz number 4 is, or will be open. Will be open. I've got a hair that keeps catching my eye, you know, when you see something. So we'll be open from December 3rd until December 5th. Same as the other quizzes. Okay. Which also means that December 3rd, we're not going to have an in-class lecture, but if you want to use that time to do the quiz, then you're more than welcome to. Just depends on what you want to do. So no in-class meeting on December 3rd, but you can use that time to do the quiz if you want to, is kind of the idea. But you could use the time to do the quiz. Okay. And all of a sudden we have no Fridays left because I made an announcement, but I feel like it was more than a week ago. I had to schedule something over our lecture time this Friday. And so I'm sorry about that, but I'll post a video and then you can watch the video. And so here, and maybe I'll bump it out and say this Friday, which is November 26th, no in-person lecture. Who knew that last week was going to be our last in-person lecture on Fridays? I don't think anyone's really that sad about it. You guys have a long week, and then it's probably nice to have a little bit of a break. on Fridays. So no in-person lecture, especially because we start kind of late. I know it's not late, but we start kind of late on Fridays. So no in-person lecture. So hopefully no one's upset about it. But I will post. I probably won't watch it. I'll make it instead, but I will post a video for you to watch. What? Man, I can't write at all. Took the weekend off. My little fingers hurt. Okay, good. I'm putting together the final project, so I'll get you that information. I don't have anything finalized because I need to check it with Joe this week, but you'll have that sometime this week, and then hopefully, I have to check with Joe, but my plan right now is to have it due December 15th, but I'm not committing to that until I've confirmed it with the head honcho. So, all right, let's see here. I didn't get through all the chapter 9 notes, the summary notes, but I did get through most of them. Just the last chapter that I didn't, or section I didn't get through. But it's going to take us a while to get there, so I'm not too worried. So today, there's a lot of theory in chapter 9, and so it's not going to be, you know, so much applied stuff, but I do want to save a day where you know, I show you some key things that we could do in R, just because that's really helpful. Now, some of this stuff when it's applied is a little bit beyond the scope of what we're doing. And so I'll just show you the key things that you'll need to finish the assignment, basically. Okay. But we have to introduce some of the concepts before we can do that. So let's see here. Now here, this is just review, okay? So just so we can keep track of some of the terminology that we're going to use here, right? We're going to talk about an observation or a record, right? And that's the number of rows that we have in our spreadsheet. And then we're going to talk about the variables. Well, that's our columns in our spreadsheet, right? And so let's see here. An observation is a row and columns are the variables. Okay. So of course, our goal is to learn about, you know, future observations based off of the variables that we've seen, and just kind of learning about the data. Okay. And so what we're going to talk about is, okay, well, what if I want to start predicting outcomes? Okay. We've seen it a little bit already, but now we're going to talk about, okay, so if I want to predict an outcome, which we saw in regression, right, when we wanted to predict out y, right, based on some variables, x1, x2, x3 potentially, right? And so we've already seen that. So when we use data to learn about kind of future outcomes, now I don't mean necessarily on a timeline future, I mean observations that we haven't seen yet. Okay. Then we talk about supervised learning when we build it off of information that we have seen. Okay. So what we're doing is we're either estimating an outcome, and that's if we have a quantitative response variable, right? Or if we have a numerical response variable, then we call it an estimation. Okay, and then we try to estimate the outcome. Whereas if we have a categorical or a qualitative response, then we call it classification. Okay, but we're doing the same thing. So in both cases, all right, in supervised learning, we predict future outcomes. We predict future, not necessarily on a timeline, right? That's what I was saying. Not necessarily on a timeline, but future is kind of the unseen. Okay, and so we predict future outcomes, and what we call that prediction or that method of prediction depends on the response variable. So we predict future outcomes, and if and the method of prediction, of course, depends on if we have a qualitative or a quantitative response variable. Depends on if we have a qualitative, which is the same as categorical, right, if you prefer, or a quantitative, which is a numerical outcome. Helps if I grab the eraser. Or a quantitative / numerical response variable. Okay. We're still predicting, right? But if we're predicting some number, right, then we call it estimation. So then we're estimating that number. Or if we are trying to predict a category, then we call it classification. Do you classify into this category or another category, right? We could have multiple categories, but usually we focus on one category that we're interested in, and then the other category would be they're not in that category that we're interested in. That's what we're going to focus on. We could, we could analyze more than one or more than two categories, but we're going to focus on just classifying between two categories. Okay, so for a qualitative response, it's called classification. Right? Which is basically saying classify an outcome as in the group of interest or not in the group of interest. Or not in the group of interest. And I'll put here that we will only consider two outcomes, right? We will only consider variables with two outcomes. We will only consider variables with two outcomes. Okay. Whereas if we have a quantitative response, then we call it estimation, right? Because now we're estimating some value. So if we have a quantitative response, then we call it estimation. we estimate an outcome. Okay. That one's a little bit easier because it's going to be a numerical outcome, right? And so we're just trying to guess what it is. Okay. So there are some key steps that we're going to go through in any sort of project, right? And we've considered a lot of these steps already, but now we have just the overview. Okay, so let's see here. If we're talking about data mining. Now, data mining is really just learning from the data, right? And we're trying to mine the data for information. Okay. First thing you're going to do is, and we're going to talk about each of these steps in more detail, but it's nice to have an overview, I think. And so data mining is just a series of steps, really. And so what we have is first we sample some data. So I guess initially you have to identify what's your research problem? What question do you want to answer? What's your goal here? Okay, and so then you can find data that helps you answer that question. You might randomly select that data from a larger data frame. And we'll talk more about that, but right. But in general, we extract some sample of the data that you're interested in, and that's going to help you answer a question. Okay. The next thing you do is the data preparation. Now, that can be, just kind of things like cleaning up your data, right? Fixing erroneous values. I think they use erroneous, and I can't think of a better word, so that's good. Identifying missing data. What are you going to do with your missing data? Now, those are all just their own fields. What do you do if you find a data point that looks to be wrong, right? Do you remove it? Do you try to fix it? Do you replace it with an estimate, ironically, since that's probably what we're going to try to be doing with it. And so that's its own field, or kind of its own chapter, I guess, or course, definitely could be. What do you do with missing data, right? Do you try to fill it in with some kind of placeholder value? Do you remove those observations completely? All of those things are things you need to justify in your data preparation step. Now, what we don't like as students, and I'm putting myself in your shoes here, is we don't like it when it's all open-ended, right? Well, how am I supposed to do this? Well, the problem is there's no one way to do it. As long as you support what you're doing, so by saying, okay, I've decided to remove these data points because I worry that if I fill them in with the average value, for example, then my values would be skewed unnecessarily, something like that, right? So you always just support your what you're doing, and then there's really no wrong answer. And I know that feels uncomfortable, but that's what it's like, right? Someone hands you a project and you just have to do it, right? There's no solutions to check against. There's no, you just need to put things out there that you feel comfortable backing up if you have to. If someone asks you, hey, why did you do this? Then you have to feel comfortable with what you did, right? Because you might have to defend it. Oof. Right? But there's no wrong way to do a lot of this stuff. And a lot of the time we try a bunch of things, and then that's how we land on something good. Okay, so so we remove kind of wrong data entries. We look at, or we might not remove them. We look at wrong data entries. We look at missing values. We look at the variables. If we have a ton and a ton and a ton of variables, then some of those might not be of interest for our question. We don't want to remove them completely because there's no harm in collecting them, right? But we don't need them for our analyses, right, to answer our questions. So then we can remove them to reduce the number of variables slightly, okay? So how we would decide which variables to keep and which ones to kind of get rid of, then we look at things like the summary statistics, right? We can look at visualizations. If you have, for example, some numerical outcome against some categorical outcome, right? Then if there's no differences in the side-by-side box plots, this is just one way that you could look at things, then there's no difference in the categories, right? So those categories aren't really going to help you say anything about the outcome. Right, so that would be one way that you could say, okay, I removed it because it didn't seem to be contributing anything to helping me estimate the outcome. Okay, you can do clustering, right? Your chapter 5 assignment, you did some clustering. And so the clustering helps us, okay, so this group is similar and this group is similar and maybe this group is similar. Right. And so what you could do is you could talk about those groups, right? Instead of talking about, you know, females under 25 who are going to university, right? You could just say, okay, here's group 1 and they look like this. Here's group 2, they look like this. Here's group 3, they, you know, generally look like this, right? And so that's one way that you could kind of summarize your data, right, is through clustering. We've touched on it just briefly, right? But the next step is going to be to partition the data. Especially when we're making predictions, we're going to need to partition the data. Okay, and so what we do is we make a training set, a validation set, and ideally, if we have enough, we have a test set as well. Okay, and so what we do, and we'll talk more about it, but what we do is we build the model off of our training data, right? And usually we build more than one model. No, always we build more than one model. And then we apply it to the validation data set, which is another set of data that we haven't used to build the model. And then from there, we pick, you know, the best model, the one that performs the best, or maybe 2 models to pick from, right? Usually we just end up with 1, but right, we apply it to this validation set, and then we apply it to the test set to evaluate how well it performs. Okay. So in order to do that, right, we have to partition the data. So usually if we have enough data points, then we would partition the data into 3 data sets. Okay. Then we build our models, and depending on what we're trying to estimate or classify, right, then that's going to determine what an appropriate model is going to be. Okay. And so you build a lot of different models, and you pick the ones that you feel the best about, right? Things that perform well. So we've seen some goodness of fit measures, right? We've seen the mean squared error, the mean absolute deviations, the MAD or the MAE errors maybe. The MAPE, right? So we've seen some of those already. And so then we can pick models from that. And then once you have a good set of models that you feel good about, then you can assess the models, right, by applying them to the validation data set. And then once you have kind of your top 1 or 2 models from the validation data sets, then you can apply it to the test set. And that's when you'll be able to see how well the model performs. Okay. So this is an overview of all of chapter 9. So I know that feels crazy, but don't worry, we're going to get into all the little parts. Okay. Oh, just as a side note, I split it here. This is kind of a forward and then 9.1, because there was so much text and just kind of information that I wanted to get out there. There's not a lot of graphs in this chapter because it's not all theory, but there's a lot of theory. So just so you know, I've run the text kind of down and I split the page in two, but this one starts here. Okay. So 9.1 kind of runs on the lower 2/3 of the page, I guess. Okay. So 9.1, it's going to talk about data sampling, preparation, and partitioning. So that's these first three. All right, so here's section 9.1. So once you have a business problem, now typically a client would tell you what they want, right? Or they might say, oh yeah, I want to learn something about my data, but they don't really tell you what. Then you have to go out and figure out what a good business problem would be, right? But here you're kind of given the problem, so you just have to solve it. But once we have a business problem, right, we have to get data. That's you know, the first step. We have to get data. And so the problem now is that we have these large amounts of data available to us most of the time, right? And so usually the problem now becomes, okay, I have too much information, but only some of it is going to contribute to my classification or my estimation. Okay, so often only some of the data available will be useful in our predictions. Will be useful in our predictions. Oh. So much text in here. Sorry, guys. I tried to thin it out as much as I could, but there's pretty much something I want to talk about in every little blurb, or I'll try to. So one thing that I want you to remember is that even though it can get overwhelming with a lot of variables in your data set, right? You know, imagine you have 40 variables that you could be using, and then you start to think about, okay, so what if I have to look at every possible combination of variables to try to predict my response? That gets overwhelming, right? And so, but it's really important that you're generally keeping as many variables as you can in your sample. Okay. And so here, so what you can do is you can use descriptive statistics and data visualizations, and then you can identify any clearly irrelevant variables that should be eliminated. Okay. You can also use those descriptive statistics and the data visualizations to address missing or data that's been, incorrectly entered or just kind of wrong. The machine was on the fritz or something like that, right? And so, so those are all options. One thing that I do want to say here is that this is really vague, right? There's no, okay, we do these descriptive statistics, right? We look at the data visualizations, right? And so in general, if there is no relationship, with, or maybe if there is no relationship between a variable and the response variable, some more vague information for you, but it'll make sense the more you work on it, right? And so if there's no relationship between a variable and the response variable, it is usually safe to discard it as long as you argue why you removed it. In your analyses. Typically, that would be something for the appendix, right? Your report should really only include important information and just kind of key insights, okay? So removed it in your analyses. Okay. So that's in general, right? One thing to look out for is, let's say, for example, that there's a variable that doesn't really have anything to do with your response variable, but maybe it has something to do with another variable, right? So it gets kind of confusing. Maybe it has something to do with another variable that does have a relationship with the response variable, right? So you want to consider, is it contributing to any of the variables really, but mostly the response variable. But I'll leave it at that for now. I think that's good enough. Okay. When we talk about a representative data sample, right, what we mean is we need to have a sample that if we draw conclusions about this or using this sample, then we can comfortably say that those conclusions apply to the population as well, right? So we collect random samples for that reason, right? And so so once we have a representative sample, which is really a sample we feel comfortable using to state conclusions about the population, so about the overall populations, population, not plural, to state conclusions about the overall population. So that is a randomly selected sample. Randomly selected, and maybe this looks like a face. So I'll just do the equals randomly selected from the population. So like I said, what we do is we split this data set. So once we have this sample that we are comfortable saying it's representative of the population, so it was randomly selected, so that's the only way that we can get there, or some version, there are more advanced sampling techniques, right? We could do a stratified random sample, we could do a multi-stage sampling, but we'll parking lot that. And let's just say, okay, once you have a random sample or a representative data sample, then we split it into 2 or 3 data sets, okay? 2, if we don't have a very large sample, then we can only get 2 data sets, okay? And then if we have a large sample, then we feel comfortable splitting it into 3 data sets, okay? So if we only have a few observations to build a multiple regression model, right, then we know that in order to get these reliable estimates, then our sample size needs to be large enough, okay? And so what we would do is if we have a small sample, right, then we would have to use all of that sample to build our model, and we have no choice, right? And so what's happening here is, let's see if I can I'll highlight that. Okay. So if the sample size is small, we might need to use the entire sample to build our model, right? We might need to use the entire sample to build our model. Right? And that's to get reliable estimates for those slope coefficients, right? If we're building a multiple regression model, then we're building slope coefficients for each variable in the model, right? And so in that case, if you have a small sample size, then in order to get reliable estimates, you might have to use them all up to build your model, okay? And so the problem is that if you had to use up your entire sample to build your model, the R² value tells you how well the model fits your current data, right? And so that becomes a problem because we built it off of that data. So that's kind of the maximized value of R², but it's not necessarily how it would perform on a new set of data. Right. And so that's what it's talking about here, right? Because, right, we built the model off of this sample data. And then ideally what we would want to do is we would want to take those models, apply them to a validation set, right? How do they perform on other sets of sample points? Okay. So let's see here. So there's this kind of, or this, I'm going to say really interesting problem that we're facing, because in the past, and for the past, I don't know how many hundreds, thousands of years, we've been dealing with a lack of data, right? And so classical statistics deals with, okay, you need to have at least this many data points in order to have reliable estimates. Okay, so we've been trained, okay, we need to have large sample sizes in order to draw reliable conclusions, right? And so here, what this comes from, right? We need large enough sample sizes to be able to draw reliable conclusions about the data. So that's a problem that we've been dealing with, and we've been figuring out, how can we do this, and how can we, if we have a sample mean, for example, what are some of the error bounds that we put on there because we have this small sample size and we want it to be reflective of the population. So that's where we've been approaching problems from for a very, very long time. But now we have tons of data, right? So now the tables have turned, so to speak. And so now we're overwhelmed with all this data. And so coming from this position of, oh, we never have enough data, so then there's this temptation that you might want to include all of it, or what we call overfitting the model. Right. And so we have all this information and we want to incorporate it all. And we try to build these crazy models. And we've talked about overfitting before. So, right. And so that's a problem. Okay. So overfitting is when you build a model that does a really, really good job of explaining the sample data that it was built on, okay? But then maybe it doesn't work as well on new samples, right? And so that can be a problem, right? So we want to find this balance of, okay, well, we have tons of data. How do I go about not overfitting, because there's a sweet spot, right, where we have just enough information that we can transfer to another sample and we can use the same information variables, right, and still get a lot of information from a new data set. Okay, so that's where we're balancing. Okay. So what we do is Minna thought I was in pointer mode, right? We split the a sample. So if we have a large sample, okay, then we have the ability to split into 3 different data sets. Okay, and so the training data is where we build our models. So this is where we build our models. I've got all these arrows going around. And I see it didn't really write properly here. To be able, there. Okay, so if we have a large sample, so if we have a large sample, let's see here. Then we can split the data into 3 parts, or into 3 different samples. The first one is the training set. Okay? And this is where we build our models. Build our models on the training set, okay, to identify maybe 10 models that we feel are the best model. Okay, so we are going to build a ton of different models here. Okay? And just little tweaks along the way. You only want to change one thing as you go, right? So if you have, let's say, only 5 variables to choose from, well, you could have variable 1 in there. That's one model. Your next model, you could have variable 1 and 2, or, right, your next model, you could have just variable 2, right? Variable or model. The next model, you could have the first 3 variables in there, and so on and so forth. So then you can look at all these combinations. So you can imagine with only 5 variables, there's a lot of different things that we could do there. There are a lot of different models that we could do, even with just linear regression, where we add them in linearly. Okay, so we build our models on the training set. And use goodness of fit measures, right? So, and use, yeah, let's say goodness of fit measures. Oops, that should look, I'm not going to say what that looked like it said. Goodness of fit measures to identify, you know, maybe a top 10 models. To identify the top performing models. Maybe top 10. Okay. The second set is going to be your validation set. Now, one thing that I do want to add here is that the training set is should be your largest of these sets. So you're not going to split the data equally. Usually your training set, and I should add that here, the training set should be the largest set. Should be the largest set. Okay. Because we still have that hang up of, okay, well, we need large enough samples to be able to have reliable estimates. And so we make the training set our largest set because that's where we're building the models. And then we're checking the models in the validation set and then in the test set. So the validation set we apply the top performing models to the validation set to identify, you know, probably the top performer. And you can do it a couple of times if there's a tie or something like that. But sometimes there's going to be an obvious top performer, so that's good. But you might have to play around with it, right? And then in your analyses, right, you would justify which one you chose, maybe because it was consistently performing better, right? Maybe you have a model that sometimes does really well and sometimes doesn't do as well, right? We favor consistency, for example. All of this stuff there's a lot going on here, right? And so, like I said, I'll show you guys kind of what you need to know in terms of applications, but not today because I don't have anything prepared for that. We have to introduce the concepts first. So the validation set is we apply the top performing models to the validation set. Now, the validation set is not the one that we built the model off of, right? So here we are applying our model to a data set that it hasn't seen before, right? And then we still know the response, right? So we know what happened, and then we know what we would have predicted to happen. And so we can compare those values to see how well it does, right? And so that's going to be our goal. So we apply the top performing models to the validation set to identify the best model. I'll put it in brackets because it is subjective, right? It depends on what you value, right? Do you value consistency? Usually we do. Do you value just, okay, this one was amazing the first round and then I don't care about anything else? That sounds weird, right? Usually we value consistency, but one of those things that you'll just have to include in your analyses, or justify, I should say, in your analyses. There's no wrong answer. So you apply the top performing models to the validation set, and then you identify, okay, here's my winning model. This is the one that I'm playing for keeps, okay? The problem is that, okay, we chose this model based off of the validation set. Okay, so then as a final step to see how well it actually performs and to be able to report how well it actually performs, then we apply it to a new set of data. So another unseen set of data. And that's where we're able to get things like an R-squared value or a mean squared error value, right? Things like that. So then the test set we apply the best model. Apply the best model. Okay. And calculate performance measures. And calculate performance measures. Okay. And those performance measures, they're the ones that you want to be reporting. These measures are the values we should be reporting. Be reporting. Nice. There are a couple of different ways that we can create our test sets and our validation sets and our training sets. And I just want to talk about a couple of different ones. There are lots out there, of course. And I don't know, I guess you could make up your own, but it helps to have something proven on your side. So when we partition data, right, that's what we're doing here. So if we have a large sample, then we can split the data into 3 different samples. And so that's the partitioning. Okay. So the most straightforward way to partition data, right, is to split into 3 static data sets. Now, remember, static just means it's holding steady, so it's not changing. So that tells us that, okay, there's going to be another method where it is changing, of course. And so the training set, right, we talked about the training set. And that's what we use to build the models, right? And so we use the training set to estimate the slope coefficients. If we're talking about a multiple regression model, it helps that we've seen the multiple regression model, right? So that's why we come back to it. But we'll talk about some other methods too. And then we can include, we can talk about the validation set. Okay, so we already talked about all these in general, okay, but the static holdout method in itself is just you split the data into just 3 static data sets, which is exactly what it sounds like. Okay. Okay, so here, right, this is where it says the validation set, right, is the one where we apply the best model, the top, 10 models or whatever, and then we identify the best model, right? And so one thing that we have to keep in mind is that, okay, if I've used the validation set to identify the best model, well, that depends on what my validation set looked like, right? And so, so that's why we apply it to the test set. Can't remember if I said that already, but that's the important thing. I will add that here, right? Depends on the validation set. Oops. Depends on the validation set. Okay, so that's the problem with the validation set, and that's why we need to have the test set. Okay. Little example, because I do find that this stuff is kind of tricky to wrap your head around in the beginning, but it is just theory for now, right? So we'll talk about what are some of the different sample sizes. So far, all that we know is that the training set should be the largest, right? And so just as an example, kind of a sidebar here, if we've identified 4 models, right, that fit the training set reasonably well, then we apply them to the validation set. And then after identifying the best of the 4 models, we apply this best model to the test set, right? And that's going to give us an unbiased estimate of the model's performance on future applications. Right. So that's the telling feature, right, that we'll be able to publish in our reports and say, okay, well, on the test set, it performed like this. And so that's why I feel it's a good model, right? Because it performed relatively well, hopefully. Let's see here. Oh yeah, sample sizes. Like a lot of things, there are no definite rules for the sample sizes of the test set and the validation set and the training set, okay? But the training set is typically the largest, okay, which we highlighted, but I'm gonna underline that here. For estimation tasks, estimation, remember, means we have quantitative response variables or one quantitative response variable. Then, so here, estimation means we have a quantitative response. A rule of thumb is to have at least 10 times as many observations as variables, okay? So if you're trying to estimate a quantitative response and you have 5 variables in your data set, then you'd have to have a minimum sample size of 50 in your training set, right? And so that's just a quick rule of thumb. Okay, not necessarily always going to be the case. Sometimes you'll have more, right? But this is kind of a minimum. Okay. For a classification task, classification, remember, means that we have a qualitative response. Okay. So now I have some categorical response with some number of possible outcomes, and then I should have at least, and I have no idea where the 6 came from, but it's probably some old rule that we're using here, and I'm sure it works, right? So then we should have at least 6 by M by Q observations, okay, where M is the number of outcome categories and Q is the number of variables. So both of these hinge on how many variables you have in your data set, which means if you have, 40 variables in your data set, well, then you'd have to have, for a quantitative outcome, you'd need to have 10 times 40, right? And so that's a large training set. And then you have to have enough data points to make your validation set and your test set as well. So that can be a problem, right? If you have a ton of variables. So notice that both of these sample size calculations depend on the number of variables. So for a large number of variables, right, our training set has to be really large. Okay, so for a large number of variables, our training set will need to be very large. Okay. So that's just a rule of thumb. And as always, there are kind of arguments that you could make, but those are kind of the rules that we're going to stick to. Oh, see, it's a little bit of overlap here. Okay, so it starts with in these cases. So I want to add in what it says there at the beginning, or what it was talking about, because in these cases it doesn't make any sense. So I should have added, for rare outcomes. Okay, so if you have something that's really hard to detect, okay, then our training set should have an equal number or a nearly equal number of observations for the different outcome variables. Okay, so for categorical outcomes or for qualitative outcomes, typically, right, then it could be numerical too, but typically we're talking about categorical outcomes. So for example, if you're advertising on a website, right, and you're looking at how many people kind of click on your ad and go to your web page or whatever you have going on, right, and so a lot of people are just going to ignore your website, right, but you're not interested in those people, right? You're interested in, so who clicked on it, right? Who clicked on my ad? Usually it's me because I slip. And then I hit an ad. Right. And so if you have a rare outcome, then we need to have a training set where we can actually see those rare outcomes. So what we do is we kind of bring them forward and kind of amplify them in comparison to what they would actually look like. Okay. And that's how we build our model. And then we apply it to a validation set and a test set, but there those outcomes are still as rare or proportionately rare as they were in the original population, right? So you only amplify, I think of it as amplifying your training set. Okay, so if the response variable is rare, right? Then the training set should contain equal or nearly equal numbers of observations corresponding to the different values of the outcome variable. Okay, so usually we're talking about a categorical outcome, right? So something qualitative. We could talk about numerical, right? But did they click on the ad or not, right? All of a sudden we have this qualitative outcome. Okay, so here I think of it as equal or nearly equal numbers. So basically kind of amplify the rare outcomes. Okay. Now you don't oversample, so you don't amplify, that's oversampling, but so you don't oversample the validation set and the test set, right? Then you let those occasions be rare. You just need to make sure that those sample sizes are large enough to be able to detect those, right? Or to even have any of those rare outcomes in them, right? And then you try to predict those, right? And that's how you gauge your the performance of your models. Okay. So the static holdout method is nice because all you have to do is you split your data into 3 parts and then you're done, right? You can apply your models and you can pick your best model, and those training sets and the validation sets, they're just static and they stay the same. So it's simple and it's quick, okay? But we know that if I were to randomly select a new training set and a new validation set and a new test set, my results might be different, right? So that becomes a problem. If I'm just doing everything with the static method, then I'm not recognizing, or I'm refusing to recognize that if I took a different test set, a different validation set, and a different test set or training set, then the model that I choose might be different. Okay, so what we can do is we can construct kind of more complex partitioning devices. Okay, and so one of those is, let's see if I can remember. Oh yeah, the k-fold cross validation. Oh. Want to grab it like this. Oh, won't let me. All right, well, hey. That was tough. So what we can do is, oh, it wasn't cut off. I thought the OB on observations was cut off. It wasn't. It's up here. So we're good. Okay, so what we can do is we can apply k-fold cross-validation. So when we partition the data and we pick a model based off of a test set, we call it cross-validation. Okay, and so what we can do is, well, if we split our data set first into a test set. Okay, so the first thing we do is step one, select a test set. Okay, so the test set is predetermined. We're just going to have a test set. We're going to randomly select a test set and put it to the side. Okay, so then what we do is we take the remaining observations, and those are going to be split into the training set and the validation set. Okay, and so what we do is we split the remaining data into K subsets. So K equal sized subsets. Step 2, split the remaining data into K equal sized subsets. Okay. And then what we do is one of those K subsets is going to be the validation set. And then the remaining K minus 1 subsets are the training set. But what we do is we change the one that's going to be the validation set until we've looked at all the different, at all K possibilities. Okay, so step 3, let one of the K subsets be the validation set, and the remaining K minus 1 subsets be the training set. Right, because the training set has to be the largest, and the remaining K minus 1 subsets make up the training set. Okay. Then cycle through and let each subset have a turn at being the validation set. So step 4, cycle through. That's the same as saying iterate, right? I find that a lot of people don't like the term iterate because it sounds like something weird and fancy, kind of, computer science fancy, but you're just cycling through, right? That's iterating. So cycle through or iterate, letting each subset be the validation set. Yeah. So what we can do, the K is the number of folds, we call them. Okay, and so we kind of have this like fold situation, I guess. And so so that means that we're looking at, okay, I'm not just focusing on letting one subset be my training set and then my other subset be the validation set, but I'm looking at, okay, overall, which model performed the best, right, out of most of these iterations, right? There's going to be some differences, but often there's one model that stands out, right? Not one necessarily, but a few maybe. Okay. What you can do, kind of a special case, is, well, what if you let your K be N? Okay, what does that mean? It means that one value is going to be the validation point, right? Because it just becomes 1 point now. And then all the other observations we use to build our model, and then we check it against that one observation, right? And then, right, I go back and I pull out another single point. I build my model based off of the new points, right? They're not new because there's just one added in that wasn't in there before and one taken out that wasn't there before, but it makes up a slightly different training set, right? And so we call that leave one out cross-validation, because we're just leaving one out. We check to see how our model performs by looking at, okay, how did it predict this outcome? And then, so it's just a special case of the k-fold cross-validation. But kind of cute because you're just checking one outcome every time. Okay. So the last thing that I want to talk about is this class imbalance data. Now, we're going back to these rare outcomes. Right, so when we have rare outcomes, what are some of the things we can do? So there are two basic approaches that we can do. Okay, so if we have a data set of 500,000 credit card charge observations, right, and 500 of those are fraudulent, right, then we have this rare outcome of a fraudulent charge. But you can see why banks, that's what the banks are interested in modeling, right? How do we pick up on a fraudulent charge? How do we pick up on spam mail, right? To be able to put it in your junk folder, for example, right? And so these algorithms aren't perfect, right? But they're built on models that are performing consistently well. And so here we have this, this rare outcome. Rare outcome is the fraudulent charge. Okay. So we have 499,500 that are not fraudulent, right? We need to have non-fraudulent data in our model because that's how it is. Right, but in terms of building our initial model, instead of just splitting the 500,000 observations randomly between the training set, the validation set, and the test set, then what we do is we can, if we're doing undersampling, for example, then we can reduce the size of the training set, right, and we can reduce the majority class observations. So basically, we just take away some of those majority observations. Okay. So versus the majority outcome, which is a non or not fraudulent charge. Okay. So we're going to talk about a rare outcome and a majority outcome. Okay, and so in this case, we reduce, so an undersampling approach reduces the size of the training set. So what you would have had, right, you could still randomly distribute, and then you look at your training set and say, oh, okay, I'm actually going to take away some of these majority outcomes because I want to amplify those rare outcomes, right? And so we consider fewer majority class observations in order to balance the classes. Okay. And so if we have a look at 800 observations, for example, then our goal would be to have roughly 400 fraudulent charges and roughly 400 non-fraudulent charges. And then that's what we're going to use to build our model. Okay. So the validation set, that's what I was saying. I'm like, hey, is it different? No, it's not different. So what we said was, okay, we adjust our training set, but we don't adjust our validation set and our test set. So the validation set and the test set are constructed to be representative of the original data. How can I highlight this? Double there. Oh my gosh. And then the oversampling approach is when I pretend to have more of those rare outcomes than I actually do by duplicating them, right? So I just pretend that there's way more. I would probably go for the undersampling approach, but I see I'm out of time here. So that's the difference between those two. So if you have rare outcomes, then you're going to need to deal with that before you can proceed. But I'm all out of time and I'm sorry for keeping you. If you have any questions, let me know. Otherwise, I will see you on Wednesday.